Today, I'd like to introduce Alec Krenzel. He's going to be presenting Decentralizing Software-Defined Networking, the Hidden Complexities of SDN and what we can do about them. Alex is a fourth-year PhD student in networking at UC Berkeley and a senior researcher at Google and the Systems Research Group. And kind of a short trip, he traveled here all the way from Berkeley. It's probably a lot shorter than most of us have here. And much better weather, too, at this time of year. But anyways, yeah, this is Alex's first time presenting at NANOC. So welcome to NANOC, and it's a pleasure to have you here today. So welcome, Alex. And I'll let him take it away.
Great. Can you all hear me okay? Yeah, great. So thanks so much for the introduction. I'm really excited to be here to talk to you all about our work on decentralizing software-defined networking. Now, this work was done with my colleagues at Google and UC Berkeley, including Sylvia Ratnasamy, Anis, Rob Shakir, Ali Al-Shabibi, and others. Now, I wanted to first give some context on who I am so you have a sense of why I am talking about the things that I am. I'm a computer science PhD student at Berkeley in my fourth year, as the intro said, advised by Scott Shanker and Sylvia Ratnasamy. But I'm also a senior researcher at Google in the Systems Research Group. And I, before that, spent coming up on 7 years at Google across YouTube, cloud, and ads now, in addition to research. And I do a number of different things in my research, but for this talk in particular, I'm going to focus on my research on wide area network control system architectures. So in this room, I know I don't need to convince any of you of the importance of networking. We all know the role that wide area networks play in enabling planet scale computing. But outside of this room, this becomes perfectly clear when outages happen. And suddenly people start to care because these outages have huge user and customer facing impact. And we see them across all of the major cloud providers. Now, we observe that these outages continue despite decades of experience and a vast literature of best practices. So the fact that minor outages continue to happen is fully expected. Small issues are going to happen. But the fact that we still have large outages is more surprising and should perhaps be concerning. And having looked at the root causes for these outages, I'd love to give you a single kind of clean majority root cause category, but in reality, there isn't one. But from looking at them, I can tell you that they're rarely about the loops, dead ends, and protocol configuration bugs that at least the academic community seems really focused on designing tools to solve. Rather, experience shows that they're often fairly complex root causes that are cascading across multiple components. So I'll give you an example of one such outage. One outage we saw at Google, there was a latent bug in the job scheduler that was running our dedicated control jobs for the network. And a completely unrelated maintenance operation typo ended up taking down a large chunk of our jobs that were controlling the routers in our network. And so as a result, traffic fell back to shortest path routing, which caused congestion until the controller jobs were able to come back up. Now, it's not these specific bugs that are important. Rather, it's that these are emblematic of the complex root causes we see for many of our outages today. So in this work and in this talk, we aim to tackle these outages by considering what we can do differently at design time to limit the occurrence of these complex failures. Now, network practitioners, you all in this room, do have techniques for trying to prevent this today. These include techniques like isolation, where we shard or partition the network to contain the blast radius of anything that goes wrong. There's diverse redundancy, in which we try to minimize single points of failure. The academic community is very interested in formal verification, in which we model the network in some sort of formal language, and then exhaustively search it for all possible packets or flows to try to prove that no traffic is going to be mistreated. And yet, these outages do still keep happening. They're in the news. So to the extent that there is a generalizable root cause for these large outages, we observe that it's perhaps the complexity of the architecture and the interaction between the components in our architecture. So in this work, we're going to look at simplification as a possible technique to help. Now, I know intuitively as systems people, we all understand the virtue of simplification. So to make this more concrete, the question I'm going to be asking is, what components can I take out of my control plane and out of my network while maintaining the functionality, performance, and cost that we've come to expect from our networks today? So through the rest of this talk, I'm going to give you an overview of what SDN WAN architectures look like today. It's the ones I'm familiar with. The opportunities we see for simplification, our approach, which we call Decentralized SDN, and an evaluation of dSDN's performance. And hopefully I'll convince you that dSDN is the right architecture going forward for software-defined networks. And I'll take a few slides at the end to talk about some adjacent upcoming research on this thread. Okay, I'll start with background, which is the networks run with SDN today evolved from the protocol-based networks that we all know and love, which rely on protocols like ISIS, BGP, and RSVT to establish connectivity and maintain it in the face of network failures, link cuts, routers going down, etc. But decades of using these protocols have shown that while they were survivable, they have their own challenges in managing, scaling, and evolving networks. So over the past 15 years, some large-scale wide-area networks have shifted to SDN-based architectures, which have a single central control program, logically single, written by the network operator that's responsible for reading the network state, computing new paths, and programming those paths back into the network. But despite this conceptually simple diagram, the reality is actually much more complex. So first, to handle global scale, the control program is in reality hierarchical, with intermediate control jobs spanning the globe, providing aggregation up and down. Then all of these control jobs require running on a network operating system, which runs on dedicated physical hardware in data centers around the globe, managed by some sort of cluster management software. Then for these controllers to actually reach the routers that they're supposed to control, we rely on a dedicated out-of-band control plane network that likewise needs to span the globe, the same footprint as your network. Then collecting and providing abstract inputs to the controller that are necessary to figure out what the new paths should be necessitates running dedicated topology and demand services. And finally, perhaps worst of all, to handle any potential disconnection between the control plane and the data plane due to failures in any of these components, we actually keep running the same traditional protocols that we claimed to have moved past as a fallback, as an inoptimal but in-band fallback. So taken together, the shift to SDN has given us a whole new host of external dependencies while actually still maintaining the old, potentially undesirable dependencies on protocols that we claim to have moved past. All of this makes for more than just a complex diagram. It's also reflected in our outage data. So we see it over the past 4 years, more than half of our largest outages were root caused to issues either in the control plane or the control plane infrastructure. So this actually matters. This complexity matters. Okay, so my claim to you is that we're going to look to address this class of outages through tackling complexity head-on by aiming for simplification. But you might ask me, why not go back to the at least infrastructurally simpler world of distributed protocols that we all know? Now, this is something we can't do because SDN has given us benefits that we've come to rely on. These are, namely, being able to run operator-defined code, which enabled operator-driven innovation, the ability to have that code run optimized TE computations on a global view of the network, which lets us utilize our network more efficiently, and the simplicity of consensus-free path selection that comes with having a single authoritative decision for the path that any packet takes through the network. So our goal is going to be to simplify while retaining these benefits of SDN. And we see a way forward through recent router ecosystem developments. So first, over the past few years, all of the major vendors have begun to support running third-party containerized code directly on the box, which, as a result, enables our operators to run custom control code on the router CPU. And second, we've seen over the past few years a new generation of standardized control and configuration APIs reaching maturity, which expose router telemetry and router configuration in a vendor-neutral way, which allows for our control code to be entirely uniform across vendors. And finally, we've seen expanded on-CPU router resources. So over the past few years, this has culminated in multi-core, multi-gigahertz CPUs dedicated to the control plane. So taken together, it's now become both technically feasible and operationally practical for operators to run control applications directly on their routers. And this is what we're going to use. All right, so observing these trends and the large fraction of outages that we claim are rooted in control plane complexity, we propose our essential idea to fix this, which is a system that decentralizes the SDN control plane. Now, in order to do this, we take this external controller and we move it in-band by replicating it onto every router, which then allows us to get rid of the complex hardware and software infrastructure that was previously required to maintain an out-of-band controller. So more concretely in our design, every router runs a dSDN controller on the box in a container that first floods its local state so that everyone can learn the global view, then locally computes all paths using an operator-specified traffic engineering algorithm, and then finally programs just the subset of paths that originate at that router using strict source routes. So let me make this more concrete with a walkthrough, an example. So in a network like this one, with these 5 nodes, first each router reads its local state and produces a node state update that contains information about which links are up, but also demand information. Now, you'll be correct to point out this is very much like ISIS or any traditional link state protocol that you know, except we've built these updates to also include demand, and we've happened to build them over gRPC connections that are established between adjacent dSDN controllers that don't rely on existing network connectivity. But this allows all routers in the network to build a global view of both topology and demand. Next, each router is going to run a global TE algorithm to compute all of the paths. I again want to point out, this is similar to what something like ISIS does, where ISIS runs Dijkstra's. But instead, here we're running a full TE solution that's looking to compute the globally optimal set of paths across routers, assuming they're collaborating. And that TE solution is defined by the operator. And then the router encodes just the subset of paths that originate at that router as strict source routes. It ignores all the other ones. It computes all paths, but only programs the ones that originate there. Okay? And now finally, when it comes time to forward packets in the data plane, it's very simple. Forwarding just follows the source route specified in the packet header, which is written at the ingress router. So when a packet like this one shows up to your network, you look up in your forwarding table the destination, you find the source route, it goes in the header, and then every router along the way just pops the outer label, looks at where it should forward next, and the packet continues on to its destination. So I want to call out here and point something out. It's our decision to use strict source routing that maintains simplicity in the face of decentralization. And this is because strict source routing allows the ingress router to dictate authoritatively what path the packet is going to take. So as a result, to program a path, you need no coordination across routers. A single router decides that path and specifies the path that should be taken at the ingress. And we also, so no consistency required, and we trivially stay loop free. So in this way, traditional SDN, which I'm calling CSDN, and dSDN are actually kind of similar. In both, there's a single authoritative decision maker for every path. Just in CSDN, it's the central controller that's authoritative for all paths, whereas in dSDN, it is the originating router controller that's authoritative for that path. Okay, implementing strict source routing requires enumerating the full path in the header. And I'll point out, this has been historically infeasible due to the length of WAN paths and the router hardware available, like how much of the header is actually visible when we go to forward a packet. But in our work, we enable this source routing through a combination of newer chips, which allow actually reading further into the packet, but also a novel encoding scheme, which allows us to kind of pack in multiple hops in each label. I don't have time to talk about it here. You can see it in the paper. All right, so taken together, moving the control plane back onto the routers, dSDN cuts out a huge fraction of the control plane infrastructure, which we started off claiming was a root cause of a non-trivial amount of outages. And furthermore, it restores the survivability that was lost through centralization that necessitated us continuing to run traditional protocols as fallback. So as a result, we have a much smaller surface area for bugs, and we greatly decrease the number of components on the critical path for routing. All right, here I want to take a step back. And I want to see if this design achieves what we set out to achieve. The original benefits at SDN that we aim to maintain were running operator-defined code, which can run optimized computations, and maintaining the simplicity of consensus-free path selection. And we see that with this design, we get all three. We run operator-defined code by running our own containers on the router. We're able to run optimized computations on a global view of the network, using the global view that's collected and distributed entirely in-band. And we maintain the simplicity of consensus-free path selection by using strict source routing, because each of the head-end routers can authoritatively dictate what path packets take. But at the same time, we also get the benefits of decentralization, which are namely drastically fewer external dependencies because our control plane runs entirely in-band, and we get distributed survivability because there's no single central point of failure. Now, I had this slide to compare central SDN to dSDN. I also thought I should compare this compared to kind of traditional protocols, because that's what is actually used in practice in many more networks. And so compared to your traditional protocols, the dSDN architecture gives you as the operator full control over the traffic engineering and the routing decisions that you're actually making, including the ability to do global optimization, so globally optimal traffic placement, but using just the routers that you already have running in your network today. You don't need to go and build any additional hardware or software infrastructure to run controllers, to connect those controllers to your routers. And so in this way, we think you get the best of both worlds. Okay, our primary goal in this design was to decrease the number of outages, right? And our thesis for getting there was to cut complexity from the WAN in the components that we claim were potentially causing outages. And in an ideal world, I would love to go and run dSDN side by side with a traditional SDN for a few years and report back to you and tell you there are fewer outages, 50% fewer outages. That's all very wishful thinking as an academic. But instead, I can certainly just point out to you that at least from the design side and the implementation, since we built this, we have achieved cutting complexity. We're removing all of those components on the left, while maintaining the performance that we expect from our network, and the functionality we expect. But the next question we asked in our evaluation was this: have we lost any performance in the process? And surprisingly, on the contrary, we find that simplification actually improves your performance. So in order to evaluate this, we built a production-grade implementation of dSDN. And about 22,000 lines of Go and another 7,000 lines of C++, which was the first couple of years of my PhD, forward into that, which we then ran and profiled on Arista 7808 production grade router in our test lab. And what's kind of cool, having been also at Google at this time, is I could go and take the exact same inputs that Google's central SDN controller takes and feed them into my controller running in the test lab on the router. So the exact same inputs, streams kind of in parallel. And then I also could go and profile the central SDN controller and measure its performance so that we could compare. And then to understand the behavior on particular events, like when a late cut happens, how do these two architectures react? We went and replayed particular historical failure events in a high fidelity event-driven simulator for both CSDN and dSDN's behavior to compare their performance. And through all of this, we evaluated two core facets of WAN performance, which are the time it takes for a control plane to converge and the impact to traffic, what your traffic actually experiences during that convergence. And so we're all on the same page of what convergence actually looks like. We can break down convergence into three kind of chunks, three periods. First, during propagation, the controller needs to find out what the state of the network is, what's going on in the network. So in CSDN, this happens out of band. Every router kind of streams up what it knows about what's happening, links that are up or down, demands, etc. Oops, there we go, up to the central controller. Whereas for dSDN, this happens entirely in band through flooding. Routers just flood their information and everyone's listening, just like a traditional link state protocol. Next, during computation, the controller is responsible for computing new paths that traffic should take. And in CSDN, this obviously happens on the controller, which is running in a data center somewhere on some very great compute. In dSDN, this happens on every router in parallel. All routers are running the same global TE, the same algorithm, solving for all the paths with the same information that was flooded. And finally, during programming, the controller is responsible for reflecting these updated paths back into the network and telling every router what to do. And in CSDN, it's the central controller's job to make this happen. And I want to point out something kind of surprising, at least it was surprising to me when I was doing this work. This is actually a pretty complicated operation for the central controller to orchestrate and control. Because as it comes up with new paths, it has to first go and tell all of the transit hops to install their new forwarding entries for the new tunnel. Only then can it go back to the head end, to the ingress router, and say, switch over to the new tunnel, and then go back and remove the old entries that were no longer needed. So it's this two-phase series of, that actually takes quite a while, and we break it down in the paper. Whereas in dSDN, because we're using strict source routing, all of the programming happens entirely locally. So you just say, this is the set of labels that you need to put in the header for your packet for this destination. So now to show some actual results. We measured each of these components, and I'm going to put up some graphs here. I'll note here the differing axes. The left and right graphs have are not linear. The central graph is linear in its axes. But what we found is that dSDN's convergence time is actually a full 2 orders of magnitude faster than traditional centralized SDN. And I'll point out why. Even though the computation time is slower, because, and this is not a surprise, the compute resources you have available on a router are definitely less than what you would have in a box running in a server in a data center. So yes, dSDN is slower at computing paths. But because propagation and programming happen entirely in band and locally, the end-to-end time is actually much faster. So the gains that you see in propagation and programming time actually far outweigh the slightly slower computation time. I'll point you to the paper here for more details. I'll link the paper at the end if you're curious to take a look at a technical report for any of this, where we break down why programming time and propagation time are so slow in a large global WAN. Okay, now for convergence impact. Convergence impact has to cover both the amount of time and the number of flows affected, right? Because I could come up with a solution that is faster at getting to converged state, but during that convergence period is actually way more disruptive to your traffic, drops a bunch of traffic. And that's definitely worse than something that takes slightly longer, but treats your traffic to kind of gracefully. And so we kind of, to capture this, came up with this metric, bad seconds, in the paper that covers both. There's a bunch of numbers in the paper. I'm going to just highlight one set here, which is the bad seconds that we saw at the 98th percentile. A percentile over what? We ran 1,000 days of simulation of running both CSDN and dSDN using production kind of streamed data. So what would have happened if we had run dSDN instead of CSDN on our network? And you can just see the numbers, the bad seconds for dSDN are considerably lower than CSDN at the 98th percentile. And we saw this across percentiles and across a priority class. Intuitively, I'll just point out, it really is all about converging much faster while still handling traffic just as gracefully as CSDN. So we kind of see the same little spike in impact during convergence, but it just happens in a much shorter window. So not super surprising there. There's many more details in the paper. So beyond the quantitative performance benefits, we also wanted to look at qualitatively what additional capabilities dSDN enables as a platform for on-router applications. And And what such capability we looked at was the fast reroute protection mechanism, so FRR. Just curious, are people familiar with FRR here? Yeah, it's a common thing that we... True, many different FRRs. I'll describe what I mean by FRR actually so that we're on the same page. When a link cut happens in your network, you don't want your traffic to just get dropped while you're waiting for your kind of control plane to recompute and program new paths. And so the FRR mechanism, the one I have in mind in particular is like RSVPT's link protection mechanism when it establishes tunnels, is to set up for every link a backup path that says if this link goes down, any traffic that was supposed to go on this hop should actually go on this little backup path around that downed link and then continue on in its path. So that when a link cut occurs, that backup path can be enabled and traffic just continues to flow. Now, these backup paths, as I said, are established typically for each link hop and at the time when an end-to-end path is set up. And many different policies for how to do this. One might be just pick the shortest path around that link. But because these are very rarely used, we only use them when failures occur, there's no capacity reserved for them on these links. No capacity reserved on 1 to 3 and 3 to 4. So while this normally works well, the problem is in reality, these links are constantly fluctuating in their utilization. And so maybe when this backup path was established, 1, 3, 4 was actually a good backup path. But as utilization shifts, if a link failure happens at this point, all of the traffic that was supposed to go on that middle link is now going to fall back to this backup path, and it can overwhelm this link. This link can get overutilized, causing congestion and packet loss. So the capability we were looking at was you have a dSDN controller that's running in-band on the router and is fully aware of the telemetry in the network. It's aware of the utilization, it's aware of demands, etc. And so it can proactively look and move backup paths at runtime as link utilization fluctuates, so that when a link failure does occur, traffic falls back to a less utilized path, resulting in less packet loss. So in order to evaluate this, we went and looked at a 2-week period in Google's network and looked at the top 6 bypass congestion events. So congestion caused by exactly the scenario I described to you. And we implemented a couple of different algorithms that you could run with information that dSDN has. There's a bunch of numbers in this table. The ones I'm proud of are the ones on the right, the zeros, which point out and say that for all 6 of these scenarios, dSDN was able to fully eliminate your bypass congestion by just periodically running and checking what the utilization of links is at the time and moving these backup paths. Again, lots more details in the paper. Since I have time, I'll just point one out. This doesn't come for free, right? The downside is if you're trying to move backup paths, you might get some latency inflation, right? So in the parentheses there, I have numbers that are 1 point something. That is how much longer the latency of the flows were, the paths, because we ended up routing traffic on a slightly longer backup path that was less utilized. So, okay, you maybe see some latency inflation. My claim is that this is much better than dropping those packets. So I think this is an acceptable trade-off. All right, so we examine a bunch more questions in the paper that I don't have time to dive into today. These included looking at how dSDN scales with larger topologies, which we showed scales pretty well, actually. How it handles networks that have higher churn rates. So when more things are going wrong, how well does dSDN react to those quickly? We look at other benefits to having a controller in the loop. And we also discuss how you make source routing work for very large networks. So yeah, definitely encourage you to see the paper. Now, I've presented a few different applications here for you. So namely, full routing, full traffic engineering, and doing smart FRR bypass routing is the one I just talked about. But there's many possibilities for things you might want to run on a router if the infrastructure exists. You could imagine an auto repair agent that's kind of running on the router and watching and trying to detect when something goes wrong. Maybe at that point we should drain the links automatically. Or you can imagine telemetry validation. If your router ever produces bad data, you might be able to detect that locally before sending it up to whatever control applications you have. So having developed and run dSDN for a couple of years now, we found the dSDN architecture can act as a platform for a variety of applications. And there's more exciting ongoing work applying dSDN to other applications I hope to be able to publish on soon. But you might have some ideas of some applications you yourself might want to build in such an architecture. So I thought I would just highlight, for those interested, we had to build some infrastructure to make this possible, and we've open sourced some of it. Kind of the most useful thing is perhaps Container-Z, which is part of the OpenConfig standard now and is a vendor-neutral way to orchestrate containers on device. So to deploy, start, stop, list, and log your containers. We also extensively relied on GNMI for vendor-neutral telemetry reading. And there's a couple of other things also that we describe in the paper and elsewhere. So in summary, on this work, we've spent 30 plus years trying to kind of fix and evolve distributed protocols to add more features to support the needs that we have as operating a large network. And we've spent the last 15 years trying to make SDN-based networks more reliable. And in this work, we're presenting dSDN as a new point in the design space, and one that we claim achieves the best of both worlds by decentralizing the SDN controller in a way that maintains the benefits of SDN while significantly simplifying the control plane infrastructure and improving convergence behavior. I have up here a QR code and a link. If you're interested to see the paper, we published this a year and a half ago at SIGCOMM. It's a 14-page paper with all the details. But while I'm here, there's another bit I want to talk to you all about. So I mentioned at the start of my talk that I'm a PhD student. Across the bridge, very short commute for me. My goal in speaking here was actually twofold. So first and foremost, I definitely wanted to share a research vision of what I think SDN should look like and what we can improve. But equally importantly, I'm personally very interested in facilitating, encouraging more interaction between academic researchers and the actual people that work on networks. The network operators and architects and engineers all here at NANOG. You know, it was very interesting for me in our academic classes on networking. There's a very clean story taught of there was the world of protocols, and then SDN was designed, and then suddenly everyone moved to SDN, and we no longer have to think about protocols. And then you go and talk to people who work on networks, and that's not true at all, actually. Most people are using protocols, for example. And that's happened with a number of other projects where I see discussion about formal verification, and then I go and talk to people that actually work on networks, and people say, we're not using this, and we're not using this for these reasons that I think academics aren't thinking about. So with that in mind, I want to share briefly some ongoing research that we're doing on closely related questions in the hopes of engaging more with the community, specifically on network verification and validation. So the first thing I'm going to mention was born out of this dSDN project, which was someone coming up and asking at a talk, what cases kill dSDN? Where would dSDN fail? What could go wrong? And someone asked me specifically, what if you poison your input data? If one of the routers lies and actually says, all of my links are down, or all of my links are up, but they're not actually up. Well, dSDN is running traffic engineering over that global view, and so it would try to put a path on a link that might not exist. That seems like a problem. But then this got us thinking, doesn't central SDN struggle with the same thing? You have some network, you have some control infrastructure that collects up telemetry from your routers, and it takes and produces an input, an abstract view of demand and topology that's fed to a central controller. The problem is, whatever testing or verification you do on your controller that's making decisions, all of it assumes that the inputs are correct. So testing and verification can go and prove to you that for a given input, your controller does the right thing. But how do you know that your input actually reflects reality? And then going and looking at the actual outage data, a considerable number of outages are caused by some sort of incorrect input, or input that differs from reality being fed to your controller that's making decisions. So in fact, even in my diagram here, that's exactly what's happening. The little, in parentheses, input, the topology only has 2 nodes, but you can see there's 3 nodes up and running, A, B, and C. And again, the fundamental problem is, given an input, the SDN controller can't tell the difference between a bug in the control infrastructure that causes you to have a partially buggy input, or actually having one of your routers on fire, so it's not available. So our key idea in this work is to cross-check the controller inputs with low-level telemetry that's collected from the routers, checking that a particular set of invariants are held between them. Again, I'm trying to keep this to just one slide, but I want to just give some intuition on how you might be able to do that. You can go and take and read a bunch of telemetry from your routers, run some algorithms that kind of cross-check that the telemetry itself is self-consistent, and then you insert a very thin shim layer that before any sort of controller uses abstract inputs like a topology or demand, checks that they agree with the telemetry. So one example of such an invariant would be if you have a demand matrix that says there's this much traffic flowing from every router to every other router, that demand matrix should agree with your interface counters. If you have a router that says there's this much traffic leaving the network at this router, the sum of demands from all other routers to that router should equal that counter. So that's one such invariant that you could check. Okay, and actually go back here and just point out, we put out a short paper on this. There's a link there in the bottom, bit.ly/input validation. The other thing I wanted to briefly mention is model-free verification. So again, I've been going to conferences, research conferences. There's every year 2-3 papers on formal verification tooling. I'm curious if anyone here, has anyone here used formal verification in their networks? I don't think so. From just like talking to people, I've been very interested in the difference between how academics talk about networks and what's needed, and how people actually working with networks talk about what's needed. And so these techniques, they exist, formal verification techniques, take and encode your routing behavior, so how you're actually forwarding packets, into a formal model. And then they feed them to solvers that exhaustively check all possible packets, all possible inputs to your network, and try to guarantee that for every single packet, it will be delivered within some sort of performance bound. It's a really nice guarantee to have if I can give it to you. If I could tell you, I can prove to you that for your current routing, all packets are going to be fine, no matter what user goes and connects and what they try to talk to. But no one's using them, and my thesis is that this is because the models in the academic community are incomplete and don't actually support the protocols actually in use in the real world. So when I go and look at these tools, if you go and, is anyone here familiar with Batfish? Heard of Batfish? People use Batfish? Not much. Maybe some people have poked around with it. Under the, and we should talk after, under the hood, there's a formal verification model there. It goes and encodes the behavior of your, it'll simulate your control plane and say, given these configurations, what will be the resulting data plane? And then it'll encode that data plane and prove to you something. But the problem is, for example, Batfish doesn't support RSVPT just at all. So if you run a network that runs RSVPT, you can't really feed your configs to Batfish. And in fact, my experience has been taking Google configs and trying to feed them to Batfish. It can't even parse them. It just crashes, actually, because it doesn't support all the features. So my key idea in this work, and the thesis is very simple. Instead of modeling the control plane's behavior, we now have containers that actually, provided by the vendors, that can actually run, given a configuration, actually run in emulation a bunch of routers talking to each other and converging to some converged data plane. Using something like a Container Lab, if people are familiar with that, or Kubernetes Network Emulator. And then let's take the resulting data plane and apply the same formal verification techniques that exist in research to give you some sort of guarantees back. I think what makes this research kind of hard for me to do where I sit is this is kind of less sexy to the research community. They're very interested in what are the new fun mathematical techniques for modeling your behavior. But because I think they're so focused on that, they miss the actual gap that is needed for this to be applicable to real world network operators. So that's kind of where I find myself interested in my research. We have a paper on this from last year in the bottom left corner there, bit.ly/model-free-verif. We should talk if this is of any interest to you. Okay, so in closing, I think it's a very exciting time to be in networking. I'm very excited about being on the academic side of networking. I'm sure it's very exciting to be on the operator side with a huge shift in demand. And I think academia needs to engage much more with network operators. It's kind of why I'm here, and I hope to keep coming to Nanog and meeting and talking with people. So I'm really looking forward to more engagement with you all after the talk. With that, thank you, and I'll take any questions.
Hey, good afternoon. Darren Carr, Quad 9. First, thank you for the presentation. Two, I told you I'd show up and be in the front row. If you go back to the beginning, you had a pie chart and it had 4 different values, I think, as far as outages. One was like 16% for other. What falls into the other category?
All right.
Is it these bugs? Is it what is it that's unexpected or that you either throw in one bucket or can't define?
Because this doesn't work holding it down, it'll take forever to get back, so I won't go
okay.
back to it. But I do remember the slide you're talking about. I think I had control plane infrastructure, control plane, data plane, and other.
Yes.
I actually don't remember off the top of my head the examples that went into other. I might need to get back to you afterwards and pull up.
That's fine. I'll
data.
give you my contact info. I'm just
Yeah.
curious academically.
Yeah, I don't remember off the top of my head. But what I did is I went and took kind of a list of the largest outages over the
Right.
past 4 years, and I labeled each of them I specifically looked for control plane or control plane infrastructure, and I had other, and then I noticed a lot of data plane issues, so I started labeling those data plane, and I remember other being ones that didn't fall in those categories.
Okay, thank you.
Thanks. Yes.
Michael Sinatra, ESNet, speaking for myself, and some days I'm not even sure I'm speaking for myself. But I want to sort of see the whole framework, and I think this is really, really interesting. By the way, there's sort of 3 things going on. I mean, you've got some really cool goo that's basically saying here are the paths that I'm computing paths to take based on reading of telemetry, which is really the second part. I can see what the demand is out there, so now I'm going to compute paths. Then I push labels.
Yes.
Once I push labels, the network has to know what that means.
Yes.
The part about the network knowing what it means is something that you are basically programming in yourself, right?
Static. Yep.
So this is something that like ISIS with segment routing would do.
Yep.
And I'm wondering from an operator's perspective, if someone's already written something, I don't want to write it myself.
Yep.
So how could I do the cool goo, okay, using standards-based telemetry and standards-based ISIS-SR? That's what I would really like. That would be like the holy grail there.
Yeah.
So do you have you done any research onto that, or is there any way to kind of think about how that might work?
Yeah. Thanks for the question. I think I'll answer, and then I would love for you to point out if I'm answering the right question. I will say that the decision of what your data plane looks like, even though I presented needing to do this with kind of these MPLS labels, using some technique that we have to like double the number of hops you could take, the data plane decision is actually completely independent of this control plane architecture. In fact, in the way that we implemented it, the dSDN controller kind of has a module. It's very modularized. That's responsible for programming paths. And if you wanted to use SRv6 or you wanted to use some other way of doing your source routing, you're totally welcome to do so. So I think that's a great question. I'll say that I don't think dSDN kind of locks you into any sort of you can go and do this with whatever technique that fits the hardware that you have and the expertise that you have.
Okay, that's really cool.
Yep.
Thanks. Yeah, that was my question.
Great. Yes.
Hi, Omri from IceNizy. So this is more of a WAN thing. So do you see this working inside of a data center, DPU to DPU infrastructure for like a private cloud or more of a hyperscaler style solution versus a central management?
Yeah, conceptually, I could totally see that working in that environment too. I think I'd have to think about the kind of like size of how much information needs to be flooded and how often you want to be reprogramming those paths in a data center context. In my mind, when I think about data center routing, I think of kind of very structured networks that you want kind of all-to-all communication, and you want to, you don't really know where jobs are going to be. So bisection bandwidth is really important. There's kind of a separate set of concerns, but this architecture for how to actually go and program, I think is completely applicable. Yeah.
Thank you.
Thanks for the question.
Hi, I'm Ben Kearns, 00. Thank you for your presentation. I had a question. You're talking about your formal verification, and you're talking about demand matrices and telemetry.
Yes.
Can you help me understand a little bit about how that's practically created?
Right? Yeah.
Like, so like being able to model the demand utilization,
yes,
packetization, all that sort of stuff. Like, is there frameworks out there or tools that you can use? Like, is it all based on packet capsules? Like, how do you guys think of that?
Yeah, this is a great question. I discuss it much more in the paper, so the paper will be a good place to turn to look. I'll give a brief answer because I think it's really cool. It's interesting. At least how Google does this, and this is published in a paper, so this is out there. For demand, you can sample demand on your routers. I think with things like SFlow, where you're like going and picking out every 100th packet and based on that, you have a sketch. But notably, that's an approximation. If you get unlucky and you miss all of the packets of a particular flow, you don't know that it exists or its volume. What Google actually does for its demand is it has enforcer actually on the hosts, because it's running its own jobs, like in the actual host networking stack, it keeps track of how much every person is wanting to send. And then there's some infrastructure that kind of each host reports up. That's aggregated locally, reported up and up and up until you get a kind of network level view of from this point in the network to this point in the network, there's this much total demand flowing. I think that that's kind of overkill for, and not even possible for anyone who doesn't own the endpoints. So I think for those settings, people do more like packet sampling. The other thing you can do, from my understanding, is if you have kind of tunnels, if you're end-capping traffic, I think some routers have counters for the rate at which you're end-capping traffic, which corresponds to the rate at which you're sending.
Those things are not happening in like in real time. How does your network respond? Like by the time it's received those signals, how is it able to create a topology?
I guess part of your point is this is highly variable, it can be highly dynamic, and over the last couple seconds you could have a big spike in demand, but if you're looking at rates, it gets smoothed out. There's kind of a question of what rate or what window you should be looking over. So the way at least I think about this is you have a counter that's continuously incrementing, and you do have to configure a trade-off in how sensitive you want to be to spikes, which is over what window of time do you compute your rate from those counters. I agree it's an issue. For topology, the routers are, I mean, you can subscribe via GNMI or whatever other mechanism you use. You can subscribe to a live stream of telemetry of the state of each interface, which is I think what they do.
Thank you.
Thank you. One more, if we have time for one more. Last question, yeah.
Yeah, Wim Hendricks from Nokia. Yeah, great presentation. I think I want to put a little bit in context, like you compare the CSDN with the distributed SDN when you control the underlay. Right?
Yeah.
Because that's your use case. There is another type of CSDN use case, which I call the SD1 bucket, right?
Yeah.
Where you control only partially the underlay.
Yeah.
Did you also look at how that compares in that context or not?
I don't have too much to say on that other than we did look at some applications for kind of establishing additional tunnels or kind of, I think doing SD-WAN-like things, but I haven't thought much about it. So yeah.
It's not in scope at the moment, but
Yeah.
thanks.
Great. Thank you, everyone.